Before we start, I just want to remind you that tomorrow the schedule is exceptional and it starts half an hour earlier at 9 a.m. instead of 9:30. With that said, let's welcome our last speaker of today, Bogdan Zavyalov, who will talk about trace and duality of p-adic non-archimedean geometry.
Yeah, okay, thank you. Thank you for the introduction. Thank you for the invitation. So today I'm going to talk about trace and duality, well, in p-adic geometry. It's based on two joint work in progress. One with Srivanti and Emmanuel Reinecke, and the other one is Joachim Zoll and okay, so before I go to the main results, let me say the context and some old results that we want to build on the production. So the basic setup is that we start with a field K, which I will always assume to be algebraically closed for simplicity. And so this is not just an abstract field, but a non-archimedean field. And one doesn't lose much if one just always assumes that K equals C is equal to CP complete algebraic closure of KP. And then our object of study will be rigid-analytic spaces over such X, so over such K. So X over C is rigid-analytic space. Over C, and I mean, okay, I don't have time to define this precisely, but roughly it's an analog of manifolds over in this non-archimedean world. Okay, and then one can associate a top homology to such spaces by the work of Berkovich and Cooper, and the natural question is that what kind of usual properties do this ad hoc homology satisfy? And so the first theorem I want to mention. So it's due to many people, different situations, and I will specify a bit later, but let me formulate it first. So we start with X over C, which is smooth and proper. And it's assumed that it has pure dimension D. And L, maybe I should first fix a number n, p, which is different from characteristic of C, and L is an FP local system on X. The outside, well, then. There are three results I want to mention. So the first one is finite, and so a top homology of the system L, of the local system L, are finite at p vector spaces. So H I S L. So the second one is that there is the so-called trace map. So it goes from H to D, X with coefficients N of theta twisted into N. And the last and maybe the most interesting example, the most interesting thing is that this trace map induces a perfect variant. So let me formulate it more precisely. So the last one is that we have H I X L. We take tensor product with H to D minus I X L dual. By cut product, it has a map to H to D of, sorry, take twisted by D to D and X L, then D. So then we compare, well, L with L dual, so this has a natural map to H to D of X plus coefficients D. And this admits the trace map to FP, and so we ask that this pair is perfect. Okay, and so for this theorem, there are two essentially orthogonal cases. The first one is that if P is different, if P is different from the residue characteristic of C, then this theorem is kind of easier, and the proof vaguely follows the algebraic proof. But if P is equal to the residue characteristic of C, so the theorem becomes much harder. So let me give here proper attribution. So the theorem is due to Berkovich and Huber. So this is do I have color? Yes. So this is P is not equal to residue characteristic. And then in characteristic P, so if P is equal to residue characteristic, the first contribution is due to Schonson. So this is finiteness. And it can be residue characteristic. And then there are for duality, in the case of P equals residue characteristic, first of all, it was announced by Gabor. And then in my thesis, I wrote down a proof based on kind of his ideas, and then another proof was given by Lucas Knight in his thesis. And so this is duality. P equals residue. And so so the proofs kind of the global strategy is somewhat similar, but the details of two proofs are extremely different. But in either of the proofs, the ideas are very different from the proofs of Berkovich and Huber. And moreover, somehow both proofs are slightly funny because I mean, an analog, like an oversimplified analog of what happens in all of these three proofs would be that, like, in complex situations, if you want to prove Poincare duality, you first prove Poincare duality for D modules, and then you develop kind of proper recursion of Riemann-Hilbert correspondences, and then you deduce it like just usual singular duality, which seems a bit funny from the classical perspective. And so one of the goals for the day is to explain a new proof of this result, which is somewhat more étale, and also it works uniformly. But before that, let me make some remarks. So the first one is that if P equals residue characteristics, there is no local version. Characteristic of residue. So there is no local version. And I mean, it doesn't happen for some strange reasons in some space, like there is some like overly complicated space or overly complicated local system. It happens already for the trivial constants, for the constant local system, and the easiest example of rigid space, which is one-dimensional closed unit disk. So if that's just D1C closed unit disk. So one can check that typical homology of this coefficients in FP. They behave in the following way. So if I is equal to 0, it's just FP. And if I is equal to 1, it's some huge group. In particular, infinite dimensional, and it depends on the ground field and so on. So it's kind of as horrible as it would be almost. And then it's 0 in higher dimensions. And compactly supported homology behave also like in a bad way. So it's 0 I equals 0. Then it's also 0 if I equals 1. It's huge I equals 2. And then 0 I figure 8. So, and somehow from this you can see that there is at least no hope on the Poincare duality. There might be something more smart, but the A version certainly fails. Okay, so there is no hope for this. And another question that one could ask, and that I hope to slightly address today, is that what happens for uniform systems? So here we consider torsion coefficients, and in algebraic geometry there is not much difference. Well, it's usually to some extent easier to understand rational local systems as opposed to torsion local systems. But the situation is completely different in analytic geometry. So question. So from now on, for simplicity, let me assume that C has a mixed characteristic of 0. And so a question, what about UP locals? And maybe here I need to specify what it actually means, UP local system. So here I should mean Freud out UP local system. It's kind of a natural framework for considering QP local systems. And in the algebraic world, it would give you the usual notion of Ital QP local systems, but in the analytic world, as we will see, it gives you something else. And then the immediate problem you run into is that this finiteness statement is no longer true. So finiteness fails. In general, and essentially it's the following observation is that if you take E of the elliptic curve, so it has the uniformization by G. And we define L to be a rank one system, rank one local system, which is trivial on GM and has monodromy which does not lie in ZP cross, which is trivial on GM. And has monodromy alpha not inside ZP cross. Then you can see, well, I don't want, and probably also don't have time, then homology of this local system, it contains a copy of the ground with C inside. So then C sits inside H1. E. Okay, so maybe to be slightly more precise, I need to put here analytic gel. So, but one feature that I want to emphasize here is that like the problem which distinguishes this story from the algebraic situation is that this local system L does not have a Z equivalence, right? That's why we choose this monodromy L to be not in GP cross. So this local system L does not admit a Z equivalent. Does not admit a Z equivalent. Okay, and and also a similar example exists on P1, but it's harder to write down. Similar example. On P1, and it's also related to the fact that the Young's fundamental group of P1 of analytic is huge. Okay, so given that, it seems kind of that there is probably not much chance to generalize this nice torsion result. But it turns out that there is actually a way to do it. And so let me say something about that. So in some sense, it turns out that this copy of C is the worst that can happen. Is that it's not finite dimensional, but in some sense it's finite dimensional if you allow both C and QP. So let me give a definition. So there is like the notion of D side, which I don't want to give a formal definition, but roughly the D side of a space X is just like all perfectly equated over X. And then there is if X, so X is now rigid space over C. And we consider what I will denote by PF from the D side of X to D side of C. And instead of taking homology, I'll take direct push forward with respect to F. And then I can formulate the following theorem. Which I hope to explain today. Okay, so theorem like of the second project is that so X against Moss and Cooper over C. So pure dimension B. L is a Preutal QP system. And so then there are two results. So the first one is that this push forward on the D side is what's called, well, for all I, this is a Banach-Kalman space. I'll explain in a second what it means. Yes, part two, that there is a version of duality. And so let's generalize this. So now let me explain what it means. Well, let me give some comments and explain what it means. So first of all, I should mention a bunch of things. Okay, first of all, let me give a definition of Banach-Kalman space, and then we'll make a bunch of remarks. So first of all, I should say that, right. So a formal definition of Banach-Kalman space is just like a category of QP sheaves on the V side of a point, which is generated by GA and QP. So, well, so the category of spaces by definition minimum sheets. Which contains QP and GA. But that's kind of abstract, so let me say morally. So that's an official definition. Let me say morally what this result saying. Morally says that HI X Preutal L is built out of QP and C, like infinitely many steps. So it doesn't say that it's like literally finite dimensional SQP vector space, but it says that like it's also in some sense finite dimensional. It could be, so an example could be C QP QP plus CP plus C, or maybe something funnier, C mod modulo QP, and so on, also in trivial exceptions. And now I want to say, okay, so that's the official definition. And now I want to say that there is a lot of work, a lot of related work to this. So first of all, part one was announced by Kidlai and Liu some time ago. But as far as I understand, not the duality statement. Then, okay, I don't know where to write. Perfect. So continuation. So first of all, yeah. So the remarks. Secondly, like this, even the statement is very strongly motivated by the work of Kalmes, Gilles, and Niziol, where they prove a version of this result for trivial for constant local system, but on partially proper X. So, so in this case, X is well, let's say Stein, or partially proper. The Stein, okay. And L is a constant. So even in this case, because the Stein spaces are usually not quasi-compact, there is a difference between pro-tau and tau homology, and the theorem becomes much harder. I mean, arguably it's deeper result in this one. But at least it indicates that one can expect this kind of duality. And secondly, there is an ongoing work of Anschutz, Libra, and Lucas Mann, where they prove much stronger statement. 600 this. Related to E expert. But our methods are slightly different and maybe in some sense harder, in some sense easier. Okay, so that's kind of, so like the goal for today will be to give kind of like a uniform proof of this theorem and maybe of this original theorem, and then see that like actually a very mild modification of this argument gives you this. Somewhat surprisingly. So maybe like before doing this, I should ask whether there are any questions or whether I should clarify anything.
Sure. So in your tail-elliptic curve example, what's the H1? Which Banach-Holmes space is it?
Well, I mean, I didn't do this exercise. So.
Maybe we can do it later.
Yes. I mean, well, one thing is that like the proof will kind of, you will not know, you won't like for the proof of this result, you won't really need to know anything about this pro-adaptive local systems. Kind of, well, hopefully.
Maybe you should ask what in which category is this power?
So this is
Repeat the question.
sorry, yeah, the question is like in this category, this R form, and this is just in well, I mean you can formulate it in well in QD vector spaces on the D side. Yes.
Just to run this. BC is also close under extensions.
Yes, sorry, minimal abelian and close on this.
Thank you.
Thank you. Okay, so let me now say something about the proofs. So the first step is trace map. Trace maps. And so this so somehow the idea is that like even though this is for this crazy TP local system, so the hard work, most of the hard work will be with sorting coefficients. So we want kind of eliminate this difficulty by some kind of methods. Oh, okay. Let me start with the Thornton case, and then I'll try to explain why we can just ignore this crazy local systems. Okay. So so first of all, I want to discuss trace maps. Okay. So here is a theorem. Well, in the first part I mentioned. So so for any smooth plot separated. Okay, I mean if you don't know it, just ignore plot and separate it. F X to Y of your dimension B. And invertible Y. There is a unique way to assign a trace map. Okay, and now I want to fix some notation. So this angle brackets T would always mean D to D. Otherwise, it would be too difficult to write all the time. So trace up such that so first of all, it should be compatible with compositions. So secondly, it should be compatible with fullback. So the third one is that if F is a tau, it's just the counit of a junction. A junction between upper side and lower street. And so the last property to pin in doubt is that for P1, it should be a notification of the algebraic trace map. So the use of algebraic trace map from like SGA4. Okay, so here again, I need to do some remarks and comments. So first of all, well, this trace map, if I was partially proper, this was already constructed by Berkovich. And for many applications, it's enough, but not for all. Secondly, so this groups like this local compactly supported cohomology is pretty wild object. It's usually not finite dimensional, it's not constructible in any sense, unless F is proper, and it doesn't even commute with space change. So, but still, you have such a map. It's pretty wild. So it's dimensional. That's no space change. And the last thing is that, like, funny enough, the construction, and I'll explain maybe the main idea of the construction, it crucially uses high rank points and like a formalism of p-adic geometry. So I don't know how to construct anything related, I don't know, like in Berkovich language or like Tate language. So construction crucially uses high rank points. So now let me explain the idea of the construction. Okay, maybe I need to erase all that stuff.
Can you actually say in which categories of constructs now?
Okay, just like in tau sheets on Y.
Okay.
I think you meant R2D at lower street. Or, oh no, sorry, you built that into the definition of angle brackets. Yes, all this. It does factor through the truncation of that thing.
Yes, absolutely. Yes, so it's really a map from R2D F lower street Z and they twisted to Z. It's more convenient to write it like this. Okay, so idea of the construction. Oh, very rough idea of the construction. Okay, so step one is kind of, okay, so the idea is that, well, the main idea is that you should just not be afraid. And just like follow what they do in SGA4 up to some point. And so, follow SGA4 construction of the trace map to reduce to the case y is equal to star COC. So this is algebraically closed from the Archimedean field. And X is an atomic smooth curve. It's slightly delicate because of remark 2, but I mean, if you're careful enough, it works. But roughly, if you follow what they do in SGA, it reduces to this situation. But then somehow, then you cannot anymore do what they do because it essentially reduces to P1, and this technique is kind of less available in the analytic geometry. So the idea is to construct now to use universal compactification of this space X, and because I don't want to introduce heavy notations and like this thing which is not familiar, which is like doesn't have its analog in algebraic geometry, I'll concentrate on the case when X is one-dimensional closed unities to explain what's really going on. So, well, in this case, use universal compactification of the curve. But I mean, it doesn't tell you much, so let's do example. X equals one-dimensional closed unities. So in this case, it's given by spa of the Tate algebra. And it admits an open immersion into what's called its universal compactification. And it's also an apenoid space. And its rational part is the same, but the plus ring is different. It's O plus maxima of T. So, I mean, and here it's crucial to work in the p-adic framework because, I mean, in terms of rigid spaces, you don't see a difference because the rational ring is the same. But so the difference between these two spaces is exactly one point of rank 2. So there is a point which is denoted by V plus, it's rank 2. And this is a closed immersion. Okay, so therefore we have a third exact sequence of G lower street. G lower street mu p goes to mu p lower star of mu p on float mu p. And when we talk to homology, we get the following exact triangle. R gamma G1. Mu p goes to R gamma this funny rank 2 point. And the kernel is or fiber is exactly compactly supported homology.
Can I ask an annoying question?
Yes.
You managed to make this precise without using the words pseudo-adic space?
No.
Okay.
So strictly speaking, this rank 2 point is a pseudo-adic space.
Thanks.
Okay, and so then Hoover tells you how to compute these things. So this is actually turns out to be just usual cohomology of the disk. So this compactification doesn't change cohomology, but changes compactly supported cohomology, and this is just algebraic cohomology of its consolidation. So then you can pass to long exact sequence on cohomology, and you get that H2 of the disk is expressed as some relatively explicit quotient. So H2 compactly supported of a disk. It admits it's a rejection from H1, KV, SL, and mu p. And well, the kernel is well, really the kernel, but
Sorry, Bogdan, does mu k mean the secondary residue field?
no, just usual residue.
Okay.
Okay, and since the Picard group of the disk vanishes, so this has a very explicit description. It's just a vertical function of mod p. And this also has a very explicit, because it's just a field, right? It's just KV H cross mod p. But remember, so this is rank 2 field. So KV H rank 2 field. So it admits essentially by construction, it admits a map plus KV H cross into gamma, which is value group of the ground field times Z. So when you take mod p, so this thing is divisible, it's killed. It's divisible. So when you take it mod p, you get a map from KV H cross mod p into Z mod p. Right, so this group admits a canonical map, and I mean, it's not even canonical, it's kind of given to you. I mean, by construction. And so in order to induce a map here, you only need to check that this thing is 0. And it turns out that it's 0. In this case, it's kind of easy to check because we have an explicit control of this group, and in general, I mean, it becomes harder, but it's true. So the claim, this is it. And so it uniquely induces a map, and this is traced to the disk. So essentially, and the same strategy works for arbitrary affinoid. Curve. The only difference is that you have finitely many extra rank 2 points, and you need to do some variations over them. Of course, then you need to do relatively hard work to check that that it satisfies all desired properties. But the construction is kind of well, not so difficult. Okay. Well, okay. So that's the point about the trace map, and then well, so this you do for curves, and then you run this kind of SGA type data search to extend it to all small slots and slots separate properties. So okay, any questions about that?
So before construction, is it possible to see from these properties what the trace map is uniquely defined?
Right. Yes. So essentially, I mean, first of all, it's like really like happens in the abelian category because I mean, this thing that lives in degrees from 0 to from -2d to 0.
Mm-hmm.
So it's really a map of abelian shift, so you can check that it's unique on stocks. Then you need to check that this thing is like unique. Since it commutes with pullbacks and like taking stocks, it's it commutes with taking stocks. So essentially, like you reduce to the case where y is C plus, and then I mean again, so one and two guarantees you that the construction is also local on X. So essentially, you reduce to the case where it's X over where x is a tau over p1 to some power, and then
Okay.
well, sorry. I think what I'm mumbling is not very convincing, but the answer is yes, it's quite it's possible. Okay, any other questions? Okay, so if no questions, let me now do maybe more interesting stuff. Is it like how this could be used to prove any kind of duality statement? And that's kind of the fun part because well now we only need to draw diagrams. Okay, I think I need this.
Can I ask a question?
Yes.
Sorry. How did you get? What was the map to Z1P again? I understood this.
Oh, sorry. So this group, this is just this, right?
So I see. Okay, sorry. Yeah.
So this group is just like you can find your seed, and you this higher rank. Sorry, rank two evaluation gives you a map from the union into gamma times Z, and mod P this is Q. Thanks. Dualities. And so first, let me do the torsion case. So because the proof will be essentially the same. Well, this is the first part. So have x to y smooth proper. So well, let me use fix p for simplicity. P is inside of y cross. L F P local system. And then so the first part is that Ri at lower side of L is a local system. And the second one is that there is a duality. So lower star LD is isomorphic as well. R on lower star L. Okay, and again, so it was previously null essentially, maybe under some mild assumptions by the work of essentially the same people, so for which. So then this thing I think was proven first by Schultz and Einstein. Like heavily using machinery of perfect white spaces, and then the duality was proven by announced first. By Gaber, I guess Gaber announced most parts, and then written down by me and by another group was done by Lukas. And right, so like now I will explain a proof which almost doesn't use perfect geometry. This is like very tiny bit of perfect geometry. And the trace map, the construction doesn't use any perfect geometry. Okay, so the first observation. Not much. Okay, so the first thing is that like when you the first thing is that like this local system is kind of confusing. It's much more convenient to work with dualizable object, sorry. And so the first general claim so that D so local systems on the outside they are equivalent to dualizable objects inside. Well, maybe I should put here dualizable objects. The outside. Dualizable objects. So this is a symmetric model category, so it makes sense to consider dualized objects, and it's somewhat classical result that locally bounded local systems with the pre-coefficients are exactly dualized objects. I think this is in particular proven on Stack's project. And so really the real proof will show that this push forward preserves dualized objects. So we show that the dualizable with the dual like this. Again, maybe I should have mentioned like new proof, the proof that I explained in the first paper. Okay, so how do we do this? So, like to say that an object is dualized, we need to produce evaluation and co-evaluation data, and then essentially the idea is that trace map gives you evaluation map, and the cycle class of the diagonal gives you co-evaluation. So, so 3-1 evaluation map. And so we have this tensor product, and can take half product into RF lower star L tensor L over D. So L, you can pair L and L dual to the constant coefficient, so we can take RF lower star of pairing. So we get a map to RF lower star and p-adic, and this admits a trace map, right? If you already constructed them. So this is our evaluation map. So that's easy. And now, but to prove that it's dualized, we need to produce evaluation map and co-evaluation map and check that some diagrams commute. And so let me explain how to get the co-evaluation map now. This I need to draw the following diagram. So we have x, y, x, y. And the diagonal map. And we wish to construct a map between FT and L. That's our RF star. And so the map that is given by to us is that we have cycle class of the diagonal, which is a map of the following form. And so essentially, we can ask how we construct it, and essentially it's constructed by Gabler. And in the algebraic case, and in the analytic case, essentially the same results work. I mean, we figure out details. Let me just say essentially Gabler in this joint paper, we figure out details in the analytic situation, but essentially it's construction for Gabler. In particular, it doesn't use any duality. And so here we have Kunitz map. So usually it's difficult to have a map into the tensor product. So we need to get rid of this tensor product, and the idea is that we have a Kunitz map to RH lower star or P upper star L. Tensor U becomes the star L over D. And so the first non-trivial result is that this is an isomorphism. So this is the only step which uses a little bit of perfect line geometry. And okay, so here we first of all we have a canonical map of RF lower star and P. This is isomorphic to RH lower star of delta lower star of P. And note that when you take delta upper star of this, it's just L tensor equal. Because well, composition of delta and p is identity in delta and p. Okay. So we'll exploit it in a second. But first, I'm sorry. So let me check. Sorry, right. So first we apply R H lower star delta lower star covariant on L to get the mapping of R H lower star delta lower star L times by L. And this thing is isomorphic by the projection formula. So R H lower star delta lower star T. So I assume that the blackboard would be bigger. Well, now we can do RH lower star cycle class of diagonal tensor again. Sorry, I'm not sure if it's possible to read. Can I fix it? Maybe yes. Let me rewrite it. So this is Irish or and this admits RH lower star cycle class of delta tensor identity so instead of FP we apply to get FP we get this state twist, right? And this is fixed, and this is replaced by state twist of FP, so we get RH lower star the upper star and this was nice one. So we can work with. So there is one map that was in the wrong direction, but it was an isomorphism, so we can invert it, and this gives us a map which we call co-evaluation. Finally, to verify duality, we need to check that some compositions are equal to identity. We need to check that co-evaluation depends on identity, composition identity depends on evaluation identity, and this other one. And well, so this is a huge diagram. Like it's a huge, like you need to to do it vigorously. You really need to write like a huge commutative diagram. But after you write, like most parts will commute for obvious reasons. But the really non-trivial input that you need to use is that trace S of cycle class at any point on X is equal to 1. So this is key. And this is not difficult to check because you can check it locally. Because our trace is defined for any X, you can, like this does not anymore depends on X, so I can reduce to X equals a unit trace. That's easy, or false because of it. And so this is essentially proves Poincare duality, no, 4 parts. So it's a local system and duality, and somehow like we don't really need to understand anything about L. So that's kind of the main observation here. I mean, in the FP case, there is not much difference between FP local systems and the constant local system because they all trivialized by finite at all cover, but it will be crucial in the QP case. Well, sorry, maybe before I go to the QP case, like any questions? Okay, if no questions, I have 5 minutes, so I certainly don't have time to explain the full program, but let me spell out the main ideas. Sorry, question? No, sorry. So here is the main idea is that to consider period twin pi. So, like in this strategy, roughly the only step that was quite crucial for to the FP story is this unit formula. It does not quite hold in the QP story. So, in particular, because even if you're over a point, homology kind of could be C vector space, and if you take product over QPs and then the product of C and C over QP is huge. So you have no chance to have any kind of unit formula. So the essential idea is to replace local systems by modules over some period in PI and then go back to local systems with some procedures. So there is a period in PI on X protocol. And so it's defined in the following way. So PI of R class is functions. Okay, I have 5 minutes, so I don't have much time to explain, but you take the R content curve over R for Y, and you take functions on some affinoid open, which corresponds to I. So I is a closed interval. And so then the main theorem is that so again X moves proper. L right out to be local system. Well, over C. And R gamma right out. And let me denote by VI without points. VI of C from OC. So R gamma pro tau of X L times a VI is a coherent VI module. So you get like honest finite statement, but after you tensor with the period ring. And two R gamma right out. L go VI. It's that converted to R gamma. That's L. Then unite. So you get the non-honest Poincare duality once the tensor is VI. And the proof is essentially the same. Essentially. It was formal, so the same applies. So the only non-formal factor is a unit formula So one only needs to take care of uniform, which is not difficult. Because like I mean the important input was the trace map, which is defined for constant shifts. So you don't need to understand local systems to define trace map, and cycloclass map, which is also something which only involves constant shifts. So you can so it immediately generalizes to QP story, and then you need to check the some diagrams commute, and this is also like essentially if you do this computation, it also essentially boils down to the constant local system. So it's essentially formal. So the
Next
problem,
technical question.
yes,
Do you use any of the magic properties of BI that it's like irregular in the theory? And
no,
Okay.
just the definition.
Right.
And well, and so then to get duality as Banachal mesh spaces. One needs to combine this theorem. I'm sorry, I forgot. So this is the second project. And to get duality Banachal mesh spaces, so here is like we don't have any new contribution. One just needs to combine this theorem with the work of and Anschluss on realization of Banachal mesh spaces as some shifts in the part of the curve. So in some sense, you don't really need to know anything about right QP local systems. That's it.
For these, for these last statements, 1 and 2, do those hold for just any locally free BI module?
Yes.
Oh, can you repeat the question?
Oh, sorry. The question was whether this main theorem works for any locally free BI module, and the answer is yes.
Did you have?
Okay, well, that was one of my two questions. The other one is, can you do this in the relative setting also?
I assume so, but the
Question.
Sorry. The question was whether it's possible to generalize this to the relative setting, and I assume the answer is yes, but I didn't check the details. There are some subtleties.
Actually, if I may, like, it's kind of weird that the homology L is like infinite, but then you tensor L with BI, and it's like finite over BI. Can you give like an example or a point model to think about why that happens?
Well, it's kind of like, so really what happens is that somehow you, for any local system, you can associate a perfect complex on the bar content curve. And then, so this infinite dimensionality comes from the fact that when you take homology on the bar content curve, you can have infinite dimension spaces.
Actually, what was the question that you were answering there?
Wait, should I repeat your question?
Yeah.
Sorry. Well, right. Sorry. The question was that it's weird. Well, the comment was that it's weird that like this homology could be infinite dimensional, but when you tensor it with BI, they become finite dimensional. And whether I can give an example, I mean, the answer is that I cannot give any direct explicit example, but roughly what happens is that for any Croydal local system, like I mean, combining this BI and the Fabina structure, and you associate a perfect complex on the far content curve, and then this infinite. So this is kind of finite object, it's a perfect complex, and then when you take homology on the far content curve, you get infinite dimension.
Can't you go back to your example with the Tate curve and just turn that into anything?
So I just like I didn't prepare it, and I probably would make mistakes.
No. I mean, not right now, but in principle. When...
Yes, yes, actually, yes.
Okay, so before we end, just remember tomorrow we start at 9 a.m. That's half an hour earlier than usual. Okay, let's think about getting out.